Good morning, everyone. And again, apologies for a bit of a technical glitch to begin the show, but glad you're here. This is one of the largest shows that we've had, so it certainly speaks to the importance of today's guest, engineer Harold Orr. You've probably read a lot about Mr. Orr and his accomplishments, and we'll talk a little bit about that and a little bit more. We're very interested to know as much as we can find out about Harold and how he got into a high performance building, some of his accomplishments. And I know he's still active in the field today, so we want to learn a bit about that as well. So, welcome, Mr. Orr. And how are you today? I understand it's a bit frosty where you are in Saskatoon.
Well, you don't want to walk outside very much.
No. And thank you for joining us today here on our building conversation show. We've met online before, and I'm hoping that when the pandemic ends and we can travel, that we'll be able to meet each other in person. That would be a great thing. So
Sounds good.
sound good? That's great. A lot of people know, they perhaps read interviews with you and seen other material online. But what I want to do is I just want to start off for folks who don't know. Not only are you an engineer, a father, a husband, uh, you are also a recipient of the Order of Canada. So, to start our show off today and to give people a little bit of background, let me read the citation when you were awarded that November 27, 2017. Here's what the citation says: Harold Orr's efforts have been integral to improving energy efficiency and conservation in Canadian homes. As a housing engineer with the National Research Council, he was a key driver of the Saskatchewan Conservation House project, which led to the establishment of new national energy conservation protocols for Canadian buildings. His innovations, which include new insulation techniques and materials, air sealing and efficient ventilation, blower door testing, and heat recycling, serve as worldwide models for energy efficient housing. Pretty big accomplishments, and again, congratulations on receiving the award. I know you get that a lot, but thank you for all of the those accomplishments. We here at Passive House Canada view you as the grandfather of high performance building in our country, and we're interested and eager to learn more today. So um, I want to just really to take a few steps back with you and learn more about your background. You come from your dad was a tradesman, he was a carpenter, I understand. And is that what introduced you? That's obviously what introduced you to the world of building, the world of construction.
Yes, I started when I was about 12 years old, working with my father in the summer months. Uh, well, I wouldn't say doing being a carpenter, but a gopher. Go for this and go for that and whatever. Anyway, in 1943, my father built a house uh, for our family in Radville, or just out of Radville, and um, building materials were not available because of the war effort. And so you could buy lumber to build barns, farm things. So he bought enough lumber to build a chicken house. And we used that for 1 year. And then the next year, he bought enough lumber to build a barn. And the third year, he bought enough lumber to uh, um, put the floors in, but we didn't have lumber to put in the walls of the house. And so he had read an article in Mechanics Illustrated about um, uh, rammed earth construction. And This is an old time method of building. It's not like a sod house. The sod houses which were built here in Saskatchewan, quite a lot of them, where they just plowed the sod and they picked the sod up and stacked the sod one on top of the other and so on. But with the rammed earth construction, it was done differently. They took clay and mixed about 3 parts of sand uh, with 1 part of clay, and you moistened it to optimum moisture content, and then you uh, tamped this into forms like concrete, and uh, and you built your house. And once you got the forms filled, you could lift the forms up and put them directly on top of the new wall, and go on up for the next section and keep on going. So we built forms out of 2x8s, 3 2x8s on top of each other, bolted together with large bolts to hold it, because, and then you put in about 4 inches of this mixture, tamped it down, and then another 4 inches and tamped it down. And my job was to uh, throw the clay and the sand in the cement mixer. And when it got mixed, then we would take it over and put it in the wall, and my father would tamp it, and uh, and we built the house this way. And then he built the chicken house with a sloped roof for one side of the roof, and he built the barn with the slope the other way, and they put these two on top, and that closed in the top of the house. And so we moved into this house in 1943.
In 1943. So we're using an old technology for new purposes. And how was that house for energy performance?
Well, it was better than a conventional house because it had an extremely large thermal mass. We could go away in the wintertime, and we'd fill up the furnace, and it had a stoker on the furnace, and would run for 24 hours. And we'd go away in the wintertime, would be away for a week and come back, and it still had not frozen inside the house.
Wow.
But the walls were only about R2.
Okay.
And the result was then that when we got back home, we had to run the furnace flat out for the next 10 days or so to get it warm enough to live in.
Right. Right. So as a young man, was your first career as a carpenter? Did you start as a carpenter yourself, Harold?
Well, I didn't have any training, but I worked with my father, and of course, we did everything from the formwork and pouring concrete for the basements to building the house, putting the windows in, putting drywall on or plastering it. And so I learned there. And then when I got married, I got a job with the largest house builder in Saskatchewan, Engineered Homes. And we were working on a project in Regina where we were building fourplexes, 1, 2, 3, 4.
Mhm.
Uh, they called Gladmar Apartments,
Okay.
and we built 300 of them. And I think I sat in every last bathtub in that project because I put the tiles around the bathtubs.
Ah. So you know those buildings well.
I know those buildings well, yes.
Right. So you've got a carpentry background, and you later became an engineering draftsman.
Well, I intended started out really early. Back when I was in grade 3, I we were going home from school one day, and I was walking across about a 200 meter pasture, and I looked down. I was the last one in line, and I looked down, and there was a $5 bill lying on the ground.
Oh, that's
And I
good money.
picked, and I picked it up, and in today's money, that's worth about $350.
Wow.
And if you've picked up a $350 bill, well, you try and find out who owned it. So we did put up a notice in the post office. We found a sum of money. If you can claim it, it's yours. Nobody claimed it, so I put it in the bank, and it became the basis for my engineering to go to engineering school later.
Wow. So we can trace a lot of the foundations for high performance building around the world to your keen eye in spotting a $5 bill in a cow pasture.
Right. Yes.
I think we're all lucky that you looked down at the right time then.
Yes.
Very good. So you were you've got a background with carpentry. You've got a background as a draftsperson, a draftsman, and then you. But didn't you want to become an architect to begin with? Did you look at architect school first?
Well, I was going to university and I got in 2 years of engineering, but I was courting my wife at that time, and she was not in Saskatoon. She was in Regina. So I spent more time on the road between Saskatoon and Regina than I should have. And
Uh-huh.
I was in the a point of flunking out.
Ah.
So I dropped out of university. I had 2 years of engineering drafting under my belt,
Mhm.
and I started work then with uh, engineered homes, and
Right.
I worked over the winter and through the part of the spring. And I saw an ad in the paper from the provincial architect asking for an architectural draftsman to apprentice under the provincial architect. So I applied for the job and got it. And I worked then as an architectural draftsman for 3.5 years. And the first building I worked on is now the Royal Museum of Natural History in Regina.
Oh boy.
And one of the drawings on that has my initials down in the bottom corner.
Very good.
But I didn't do very much. The but I did get a lot of experience in terms of various types of buildings because we were doing buildings all over the province for the provincial government. Um, the uh, the hospital in Prince Albert for the mentally uh, challenged, mental hospital there. The liquor stores across the province
Mhm.
for the mental hospital in Weyburn through. I've been in the legislative buildings. I was in charge of the plans, looking after all the plans for all the buildings,
Oh
and
wow.
I was in charge of the plans for the legislative buildings. And I think I've been in practically every room in the legislative building, including up in the lantern at right at the top. You know,
Very top.
I,
Yes.
I've been up there, and
Great.
uh, I was the Joe boy.
Yeah.
So anyway,
Continuing on that role of gopher that your dad started you on in this job as well.
yes,
Yeah.
yeah.
So tell me about you decided to go back to engineering to complete your engineering studies to not be an architect.
Well,
Uh,
the architect I was working on, he left the government service and went out into private practice in Regina, and they hired a new architect, and he and I just didn't work together. And so I decided it was time to go back to school. So I applied to the University of Manitoba to take architecture,
mhm.
and they that was a 5 year course, and they would not give me any credit for the 2 years I had in engineering at the
Oh,
University of Saskatchewan. So I could go back to the university. I could go back to the University of Saskatchewan and get a degree in 2 years, or I could go to Manitoba and get a degree in 5 years.
mhm.
And since I was married and at that time had two children, we decided that it was logical to go to Saskatchewan and continue my engineering degree.
Right.
But now, instead of being at the bottom of the class, I was at the top of the class. And as I got my degree, three of us at the top of the class, the professors took us aside and said, "You three are right. You're really need to go on and get a master's degree from this." And so we decided, the three of us decided to do that.
Hmm.
And so I was in mechanical engineering, and I uh, had to pick a topic for um, a master's thesis, which had to be an experimental thesis.
Hmm.
And so I picked a topic on one of the problems at that time was when we did the calculations for the heat loss from buildings, we could calculate the heat loss through the walls because we knew the R value of the walls and we knew the temperature difference and we could do the calculations. When we could do this for the walls and for the basement, was a little more tricky because how do you handle it? Well, you handle the above ground portion just like the walls above the house, but the below ground portion you handled as a more constant temperature from the ground source. But when you came to air leakage, uh, ASHRAE had asked you to go and use a feeler gauge, and you'd feel this around the windows and the doors and measure the cracks around the windows and doors. And and then they had you put this into an equation and turn the crank and come out with a number. But the number was always too low. We knew that the houses used much more energy than this calculation. So we estimated that the heat loss had to be due to air leakage, but nobody had an idea of how much the leakage was. So I undertook to build a piece of equipment to measure how fast the air was changing. And this piece of equipment, we would take 100 cubic feet of helium, dump it into the cold air return of the furnace, allow the furnace to mix it through the house, and then we would measure and see how fast this disappeared. And as this disappeared, uh, we could now calculate then, we assumed that the tracer gas, helium, which we were using, would disappear at the same rate as the air in the house. And so we could now calculate this. And so I worked on this, and in the first 2 years I had the equipment, but it wasn't working very well. And how do you write a thesis and say this is what we did, but the stupid thing doesn't work? And so I took another year and got the thing working properly. And the result was that I published this paper at the university, and I was doing the work at the National Research Council because the university didn't have the equipment I needed, and the
Ah,
Research Council did. And so when I quit, when I got my degree, the Research Council put me on staff and started to pay me as an associate research officer. And,
okay.
and I went from no pay to $5,023 a year.
Very good. Very good. What was it like working for the National Research Council in those days? I guess you were a housing engineer. They would have called you.
Well, I had the experience, you see, of I held a second class carpenter's papers. I didn't have enough time to get a journeyman, so I had second class carpenter's papers. I had 3.5 years of architectural drafting under my belt, and I was a graduate engineer and a postgraduate engineer, and so I worked in very nicely to fit in the spaces that needed to be done at the National Research Council.
Right. Right. And what were some of the things you worked on initially for them?
Well, one of the things was they had some test huts which um, they were 4 feet by 4 feet by 8 feet high, and we put an electric heater in them, and we had different wall finish amounts of insulation and so on. We put lots of insulation on the top and lots of insulation in the floor, so we had no losses that way. And we had electric meters and could monitor the amount of energy used for each test hut for each day. And so we could do this. This was actually testing insulation.
Ah,
And I did a lot of work on that, uh, doing linear regressions of the numbers that we had.
mhm.
And with a rotary calculator.
Ah,
So anyway, uh, but we got good results from that,
mhm.
and we were doing lots of things with various types of insulation and so on.
Right. So it's your interest right from the get go, from when you were deciding on a master's thesis, seems to have been about high performance buildings, or what we call high performance buildings, or passive house buildings today. Is
That's
that
right.
that so it was heading in, and your history of building homes and building buildings is contributed to that interest, I would imagine. But what really what got you involved in the Saskatchewan, what later became the Saskatchewan Conservation House? How did you end up leading that team?
Well, I didn't lead the team, but
Okay.
uh, it was after the energy crisis in the early 70s, in
Right.
which the Arab countries decided they were not getting enough money for their oil and decided that the oil prices doubled overnight. So
Right.
you went to the gas station, and at that time we were paying about 35 cents a gallon for gasoline. And one day you went there and it's 35 cents, and the next week when you went to fill up your tank, it was 70 cents. And so, well, I didn't have enough money in my pocket, so you only put half a tank full of gas in. You complained to the filling station attendant, and he couldn't do anything because it was done all by the company. And so, anyway, at that, but it made everybody very uncomfortable with the sudden rise in the cost of energy. And the Saskatchewan government asked the Saskatchewan Research Council to um, take a look at this problem and design and build a solar house appropriate for Saskatchewan.
Ah.
Well, the man they picked to do this was Dave Ayer, and he was a physicist and had no experience in building at all. And his first thought was, well, let's get some people on our team that have some experience in building. So they asked the Saskatchewan house builders to provide a number of people. So there were several people from various housing firms that sat on the thing. They asked CMHC to provide somebody to sit on this committee. And they asked the National Research Council, Division of Building Research, for somebody, and they selected me to sit on the committee. So we were sitting on this meeting, and somebody we were having discussing this, and somebody said, "Well, uh, how much insulation should we put in the house?" And somebody said, "Well, how about R20? Because R7 at that time was the standard insulation. So we're going pretty far out, putting 3 times as much insulation in as normal." And I said, "Well, I don't think that'll do it because uh, I had seen a farmer outside of Saskatoon who had built a house using 2x6 studs and R20 insulation in the walls, and the result he was getting was not what I would have I would like to see.
Hmm.
You would think that you go to 3 times as much insulation, you should cut your heating bill down to by about 60%. But in fact, it's only cutting it down by about 30%. So what's the trouble here? The trouble here is air leakage.
Right.
And I'd found out that houses are much leakier than people thought they were. And unfortunately, they still are. Uh, the major leakage, and if you look at in the house and you look up the ceiling and so on, and I don't see any cracks or holes there. How can you have air leakage? Well, the leakage, if you look at a house not as a normal house, but uh, as if you take a cup. This room is a cup, and you put beside it another cup, and then you cut a hole through for the doorway between the rooms and so on. That's more like a house than what you normally see from the inside. And the problem is it's a space in the walls, both the exterior walls and the interior walls. And when you look at this, they're not sealed at the ceiling.
Right.
And so, well, I've been up in so many attics. I've been up in thousands of attics and crawling around and trying to find out where these cracks and holes are. And my estimation is the cracks between the drywall and the top plate average about a 1/16 of an inch, about 2 millimeters.
Right.
And there's roughly 160 lineal feet of interior partition in a house. Times 2, that's 320 feet of crack, plus 140 feet around the exterior walls. And when you put all this crack together, it's a hole as big as the attic hatch.
Wow.
It's like you left the attic hatch out.
Open. Yeah. Yeah.
And people don't realize this and don't do anything about it.
No. No.
Uh,
When was this? When were you starting to work with on this committee to look at the solar home for Saskatchewan? Is that the late 50s, 60s?
no, this was in 76.
Okay, we've moved along quite a ways. Okay, good.
In
Good.
76. I had been working from 1962 to that time, up until that time, measuring the how leakage was, and I invented first this instrument to use tracer gas to measure the infiltration, but then the equipment that we used there in today's numbers is about $5 million worth of equipment.
Wow.
And it took us about a week to put this equipment into a house and measure it for a week and then take it out. And then we did our turn the crank and got the numbers.
Yeah.
And you just can't do that on every house. And so I invented then the blower door.
Right. Right.
Because if we would blow air out, suck air out of the house, and we could then measure the pressure differential across the walls of the house, and knowing how much air we'd blown out, we can calculate back and find out how big the hole is.
Right. Is it as big as that hatch, or have we managed to fill it?
Well, it's almost as big as that hatch. I think now in current construction, they're cutting the hatch in about half.
Right.
They're better than they were, but it's not very good yet.
Yeah.
So anyway, the Saskatchewan Research Council was asked to do this. So we did some quick calculations. We knew that there was not very much solar heat available from the sun in the wintertime. So we knew that we were going to have to, if we're going to heat it with solar, we're going to have to heat hot water and store it until the winter and then use it to heat the house. And when you did the calculations on the back of an envelope, you came up that you needed an Olympic sized swimming pool for each house. But
Right.
that didn't seem to make sense. And so the question was, how much insulation do you think we should be putting in the walls? And I said, well, I think we should have at least R40 and R60 in the ceiling. And so that's what we did. And when it came to the air leakage portion of the house, I said, well, since I'm a carpenter, I will go down and personally put in the air barrier and make it airtight. And so we went, I took a technician from the National Research Council. The two of us, Jerry McCahon and I, went down to Regina and we installed the vapor barrier, 6 mil poly, and we very carefully sealed it. And when we did a blower door test, it was half an air change per hour at 50 pascals.
Wow.
So, and that's where the 0.6 air changes in the passive house comes from. Was from this. We did it the first time at 0.5, and we hope everybody can do it at 0.6.
0.6. Wow. And you would have been using product well, there's new product available today. The job would have been, or today the job should be easier to do that air sealing, would you think?
That's right. Yes. But what we did, we knew we had to have a caulking compound for sealing the poly. We had 6 mil poly. So we used 6 mil poly and we used acoustical sealant because the acoustical sealant would not harden and would remain flexible over.
Wow, good. So tell us about that house, because that house is iconic in the history of high performance buildings around the world, and anyone who's been to other building conversations I've run, I always put a slide up of that Saskatchewan Conservation House to demonstrate, to show people the DNA of Passive House includes the work that you and your colleagues did to build that building. And I always like to talk about and brag on behalf of all Canadians about the fact, the role you played in inventing the blower door.
Well, there's two areas in terms of heat loss in houses. The air leakage is which you've been talking about, but also the heat loss in the basement.
Right.
And in Regina is built on it's an old lake bed, glacial Lake Agassiz, and in Regina there's about 30 feet of clay that have been deposited in the bottom of this lake, and it's all been compressed down to about 30 feet of clay. And when you build a house in this area, the problem is in the foundation that if you add water to the clay, it expands and causes extreme pressures. And so foundations in Regina don't work.
No.
That's the best. If you ask the builders down in Regina what their number one problem that comes back with, it's number one is basements.
Mm-hmm.
And so we decided to build a house without a basement. So we drilled and put concrete piles around the perimeter and down the center of the house. And then we put a grade beam on top of this. Then we built the house on top of that.
Okay.
And so that got rid of the basement problem. And we insulated the grade beam to keep it from freezing. And we insulated the floor to keep the heat from the house leaking into the crawl space. And then we built the walls, and we built it backwards. because that's the way everything, we built the outside walls first, and then afterwards we came inside and built a wall and put it up, and then insulated the space between the outer wall, the space between the walls and the inner wall. And then we put the vapor barrier on the inside. And after we had done this, we realized, that's the wrong way to build. What we should do is build the inside wall first.
Mm-hmm.
Then we build an outside wall. We put the vapor barrier on the outside of the inside wall. Then we build an outside wall to make space for the insulation. And then we insulate the space in the outer wall and sheet it. And then we stand the wall up. And so now the structural wall is the inside wall, not the outside wall. This means that the roof trusses don't have to span so far, and the floor joists don't have to span so far. So you get a bigger house for the same dollar spent. And now having the vapor barrier on the outside of the inside wall, you'd have nothing breaking it. It's 3.5 inches away from the people with sharp knives and so on the inside, putting drywall and electrical and plumbing and whatever you put in the wall. And so it makes much better sense putting the vapor barrier on the outside of the inside wall, and then you put enough. What you have to have on the outside of that is at least twice as much insulation for our climate. If you go to northern Canada, I should say that you should use 3 times as much insulation outside.
Right. Right. So that addresses the thermal bridging. That addresses the interior room size, and as you said, it hopefully keeps the people with long knives from puncturing the vapor barrier and creating air leakage within that building. How was this viewed by others in the industry when you were doing these things? Did they think this was completely crazy? Were they excited about what you were doing? Was there industry pushback that we can't build this way?
Well, we have had some builders, very few actually, builders build this way. This technique has really not caught on.
Mhm.
And what builders do is build to the minimum of the code,
Right.
and the code says we should use R20. Well, that's what everybody does. They build 2x6 studs, and then they put the vapor barrier on the inside, and they have troubles.
Right.
And for the same price, or very often what they do is then they put 1.5 or 2 inches of styrofoam on the outside. And for the same price, I can build a double wall and put twice as much insulation in it and make it 5 times tighter at no additional cost.
Right.
But it has not caught on.
No, and why hasn't it caught on, do you think?
Well, because the builders, by and large, look at for the lowest price.
Mm-hmm. And that it's just if they can build it with more insulation for the same price, one would think that we should be moving in that direction. There shouldn't be any argument. Everyone should see the genius of this methodology.
That's
Something's
right.
happening though.
But anyway, we did have a builder in Winnipeg,
Mm-hmm.
Flair Homes, that did this very nicely. They got onto this idea of building the double prairie double wall, and they had at least 2 crews, maybe 3 crews that were building houses. This is back in the early 80s,
Mm-hmm.
and they, whenever they'd get a house ready that they could do a blower door test on it, they would invite the other crews to come and cheer or jeer depending on how the test went. And the result was that they were routinely building houses as tight as 0.1 air changes per hour.
Wow.
And
Quite something.
Six times tighter than the passive house requirement.
Right. And
And
we're talking 40 years ago.
that's right.
So clearly to build to that tightness, you don't require space age materials from, the 2020s. You that material it was around in the 70s and the 80s.
That's right. Yes.
Right.
Yeah.
Good.
One of the latest things is we're haven't done anything yet, but we're working towards it. My son works for a company building these very large warehouse type buildings that don't have hard materials on the thing. And I said to him, he said, they have trusses that are about 20 feet apart.
Mm-hmm.
And I said, from the ground up to the peak of the roof on these, they have no windows. They've no openings or anything. I said to him, that looks to me like an opportune situation for evacuated insulation.
Your current project.
And so anyway, we're just working on it, trying to, we've taken some insulation samples, they're rigid mineral fiber insulation samples. We've sealed it in a plastic container, and we then put a vacuum pump and draw it down to a very less than 10 torr.
Mm-hmm.
And we're doing tests on this, and what we're expecting to see is that you get about R25 per inch of insulation.
Wow.
So here, if we put a 3-inch insulation panel in this wall, that's R75,
Mm-hmm.
and the panel is likely has to have the building likely has to have a vacuum pump
Mm-hmm.
permanently installed, but it only likely has to run maybe 30 minutes a month or something like that.
Okay.
And it looks like, to in a rough looking at it, looks like the situation that the building will not require any heating at all.
Wow.
Simply the occupants and the lights and
Right.
will provide the heating that you require.
Right. One of the big selling features of a passive house, of course, is that we can tell people that if you have 2 adults and a dog, you can heat your house quite nicely. Thank you very much. And if it's a big house, you need a big dog.
Right.
So
That's right.
This is the perfect example of the. This sounds to me like this is the next big step for high performance buildings from your perspective. We've got we figured out the pressurization. We know what we need to do with air leakage. And so insulation, I mean, what this means in terms of wall thickness, for example, is tremendous.
Right. Well, when I built my house, had my house built by one of the major house builders here in Saskatoon, the standard insulation at that time was R7 bats. And Owens Corning had just come out with a brand new insulation, which they called the full thick bat, which is 3.5 inches thick. It was an R10 bat. And I said to the builder, I want you to use the full thick bat on my house. And he said, oh, don't do that. He said, it'll never pay for itself. Well, I said, look, I've got a number of extras. For example, I've got cathedral ceiling. I've got windows that open in the living room. I've got a number of extras, and you're pricing these out. I said, I want you to price out the extra cost for these full thick bats. So he came back and gave me a price for the house at that time, which we had built, was $18,000. And for the full thick bats, he wanted an extra $25. Well, I had and put these in, and I estimate that I saved the $25 in the first 6 months, first winter of heating.
Right.
And now I'm saving about $400 a year because I invested $25 back in 1964.
Wow. Exactly. And I've paid attention to some of the things you've talked about with your house. You've talked about how you've insulated the basement to try and reduce energy costs and how well that's worked. My house was built in 1964 here in Aurora, just north of Toronto, in a clay bed field as well. 2 course of brick with 1 inch of insulation between the exterior brick and the interior brick, and all of those gaps along the top plate that you talk about, that I've had them sealed, and a lot of it has to do because I've read about your work and these comments about that air gap in the top. So keep talking because I've got to take notes as I work on my house. And we're getting a lot of really good comments from people who are watching us, Harold, and I appreciate the comments that are coming in today. And you know, the importance, I think one of the common comments that's being made, common themes, is about the importance of, or the role of government, and what it needs to do to spark more of passive house construction. Do you have any comments about that? I know you've appeared before City Council in Saskatoon to promote passive house. What should government be doing? What can we ask them to do?
Well, the government has always looked at this situation as they said, we don't want to impose anything on people more than we have to. And so the standards that they set are for a minimum standard, not a desirable standard. They've never set a desirable standard. And but I wish we could get an economics person involved in this and look at the situation in terms of life cycle costing.
Right.
Because well, in my case, like I say, I'm saving about $400 a year because I invested 25. Well, that makes a lot of sense. But how far should I have gone back then? Should I have spent $100 more on insulation or $300 more on insulation?
Mm-hmm. Yeah.
And
anyway, what's the return on your investment, and when does it get too painful for an average home buyer to make that? $25 was a lot of money in 1964. We may chuckle at it now and see it as insignificant, but it was a good amount of money. But what more? Yeah, what more can we do? So I certainly hear you with regards to my own place and decisions to replace windows, where the experts told me if you replace all of your windows, you know, it's going to be $20,000-$30,000, and that buys a lot of natural gas, Mr. Ballard. So in other words, don't do it. But on the other hand, when I've since done it, it's made my house much more livable. So I'm saving money, but this house is much more comfortable.
Right. And particularly in our cold weather, we're noticing this. My walls are R10. Well, yeah. For the house that was built at this time, all the other houses had R7 in the walls, but I have R10 in the walls. But my wife and I, since it's minus 27 outside, my wife and I are noticing that it's nice having a sweater on.
Yeah. Yeah.
Even though the room temperature is 23 degrees, 23 degrees, we feel cold because we're radiating to these cold windows and cold walls.
Right.
And so when you build a house properly and you put R40, I retrofitted apartment building in Regina with we put R42 over top of the existing R7. And we put R60 on the roof over R25 in the ceiling. And we put in triple glazed low argon, low E, argon filled windows with low E. And you don't have this radiation effect that you're radiating to these cold walls and being uncomfortable. You don't have to put a sweater on to feel comfortable.
Until it's 20 or 30 below zero, maybe, and then you might need something. But listen, we're getting to the end, and I know I'm just watching comments and questions. Why don't we open the floor if you're okay with that, Harold, and we'll get people to pop their hand up if they have a question, and Paula, who works at Passive House Canada, will help me out as we take some questions that we'll get you to answer. Okay, so, folks, if you have a question for Harold, let's go ahead and ask him some.
Hello, Mr. Orr. Really interesting and great to see you today. You seem in great shape for your respectable age, sir. I think that I talk on behalf of everybody here who came to listen to you, sir. You are for us a building science hero and legend. And thank you for your pioneering work, sir. It's really touching to see you here today. Here's my question for you. I forgot about what was your ventilation strategy in the Saskatchewan Conservation House. What can you tell us about it, please?
Well, we knew that we had to have ventilation in the house, and so we asked Dick Van E, who was at that time working as a lab instructor at the University of Saskatchewan in mechanical engineering, asked him to build an air-to-air heat exchanger for the house. And so what he did was he built a heat exchanger that was about 2 feet wide by 1 foot deep by 8 feet tall. And it was hot at the top. He took the hot air and blew it in at the top. It went down through and out at the bottom. The cold air came in at the bottom and up through, and the warm, fresh air came out of the top. And he used strips of 1/2-inch plywood and then a layer of poly, and he zigzagged the poly back and forth. And then he provided the air. These are the air channels, and this had the advantage of using buoyancy effects in the of the air, because warm air rises, cold air falls, and when a counterflow heat exchanger, the problem I have with current heat exchangers is they're all made with cross-flow heat exchangers. And with cross-flow, about the best you can get is about 75% efficiency. And with a counterflow, you can get up in the 90% efficiency. And so he built this in the engineering lab, and then they moved it down to Regina and put it in there. And I don't know if we ever did an efficiency test on it, but my estimation was likely is up in the 90% range.
Impressive for that time, sir, I have to say.
Thank you, Alex. Anastasia has a question.
Hello, and thank you very much for your keen observations so many years ago to help guide us in your pioneering efforts. I too was third man on a crew because my dad was a shop teacher. And so he and my mom built our cottage. So I was on crew at 8 years old, learning building trades. So being a female in the trades, it's been a great opportunity. I'd just like to know, even though Mr. Ballard said we don't need any new space age technologies to obtain airtightness from when you did it in the 70s, what would you label your top 3 items that you would suggest in retrofits would be the top 3 items homeowners should adapt in retrofitting their homes?
Yeah.
Well,
To potentially achieve passive standard or something close to that.
well, I've been involved in quite a number of what we call chainsaw retrofits, and also in terms of wrap and strap. And the wrap and strap is what we do is just do the outside walls. For example, take the siding off, and normally I see this and it really bothers me. I see them taking the siding off, and then they nail 1.5 inches of styrofoam on the outside, put new siding on, and they think they've done something. They've done nothing. I almost defy them to find any result on their energy bills after they've done this. But what we've done on a wrap and strap is go out and nail a 2x4 new stud to the side of the rafter, hang it down, and make space for the thing. Then we can wrap the house with poly on the outside and seal the poly to the top plate of the wall and seal it to the foundation. We've made the walls tight, but we haven't made the house tight. And we don't get the bang that we get where we do a full chainsaw retrofit. Where we do a chainsaw retrofit is we take a saw and we cut the eaves and the overhang off so we have a neat box. And then we wrap the roof and the walls and seal the poly to the foundation and seal it around any chimney or vent stack or whatever. And then we make strapping to make space, and we add, I like to add at least 1 foot of insulation. What I normally do would be on the walls, I would use a 2x4. Well, we put framing on the roof first. We put, say, 2x8s on the roof, 1 at the edge, 1 at the peak, and 1 halfway in between, and then put new rafters. And this gives us then 7.5 inches of space and 3.5 inches of space. And we can fill this all with insulation, plus the insulation in the attic, which is likely 20 or 30 hard, 20 or 30. And so we have close to our 100 on the roof. And then to the side of the rafter sticking down, we nail a 2x4 to the side, hang it down, so we have space on the walls that gives us how much space did you put? And then we wrap the walls with poly and add all this insulation and make it the walls super insulated too. And we can do this. In fact, is we've done this where we've taken a backhoe and dug down to the footings and carried it right down to the footings of the house. So we've insulated the basement. We've made the basement tight, the house walls tight, the ceiling tight, and we've added insulation.
Great. Very good. Hans.
Hi, thanks for this session. This is amazing. I seem to remember that there was a fairly big water tank in a Saskatchewan house attached to the mechanical
Yes.
system.
Well, after we had designed the house and so on, we estimated that we could have heated the house with $25 worth of natural gas a year. This is 1977. $25 in natural gas to heat the house for a year. And we passed this information back to the government, and they said, that's fine to make it conservation, but heat it with solar energy. And so we put a crew of from the university who are interested particularly in solar together, and they designed a solar system using vacuum tube solar collectors, and they put a tank in there. It's, I think, 1,800 gallons of water, and we insulated the tank with R100, and we heated it. Now the cost for building the house, all the construction cost, labor and materials, was $60,000 in 1977. The cost of the solar system was $65,000. And to provide the equivalent of $25 worth of natural gas. And then it ges better, because for the first year, the maintenance cost on the solar system was $10,000. And the maintenance cost on the solar system for the second year was $5,000. And on the third year, the house was sold and the owner took the solar system off.
But solar is much better now.
Now, solar is much better now, but I think when you have the heat, save it. It's a much better choice.
It makes more sense. Thank you very much, Hans. Lee has a question.
I'm wondering about using insulated shutters on the windows, because a local Buddhist monastery where I'm at, they went from 2 logging truckloads of firewood to 4 or 5 pickup loads, mostly just with movable insulated shutters you could put on the window. If you're not using the room, close the shutter. It's 10,000 square feet, and they're using 4 to 5 cords of wood now instead of 50 cords. It's quite a building.
Just using insulated shutters, interior shutters, obviously, to insulate the room when they're not in it.
Well, we put shutters on the Saskatchewan Conservation House too. The problem we found was, or the couple of problems, the shutters on the main floor were hinged at the top and folded up against the extended soffit. So we had the soffit sticking out far enough so that in the summertime, the window would be totally in shade because of overheating. We didn't want to overheat the house. And in the wintertime, the sun could come in and get full sun in the shutter. And so we made the shutters so they would fold up, and they had electrically operated. And all you had to do was press a button and the shutters would open, and press the button and the shutters would close. The problem we found was that the gasketing on these shutters on the outside would not seal in the cold weather. Oh. And so the shutters were quite ineffective. Right. Upstairs on the second floor, we had shutters that slid horizontally in the wall, because the wall was very thick there, and we slid the shutters back into the wall, and it was between it had an inner double pane and an outer double pane, and you had to open the inner pane and manually slide the shutter across and then close the inner pane. And manually doing this was a pain.
I can imagine.
And it was very ineffective. So
Harold, I'm mindful of the time. We are about 16 minutes past the length of time we said we would keep you. Clearly, though, from the reaction of our audience today, there's a lot of questions people would like to have for you. But I think what we'll do is we'll end it here. I'll let the folks know that we'll post this. This session's been recorded. We'll post it to YouTube. And I'm really hoping that in the next little while, you and I can get together again and learn a little bit more, because there's so many areas I wanted to explore of your career and your life. And I know there's going to be more questions of you as our passive house pioneer here in Canada. So I will thank everyone for being on today's building conversation. I have sent you in our conversation a slide of the courses, some of the upcoming courses that Passive House Canada has to offer, that builds on the knowledge of Harold Orr and others, the pioneers of passive house building. So we invite you to join us, to take a course, to learn more, to share that with your colleagues. And we will, for now, say thank you to Harold Orr. And Harold, we'll see you next time. Now that we've figured out some of the technical glitches at our end to get you on, let's do this again.
Well, happy to do this for you.
Very good. I really appreciate your time. And as you can tell from the audience, we really appreciate your leadership on helping Canada develop these passive house standards. So I know you've got to go. Thank you very much. Take care, everyone, and have a great rest of the week. Bye for now.